So, welcome to Austin. Okay, welcome to Austin. I hope you all are enjoying the conference. I hope you all are enjoying the town and the warm sunshine. I know some of you came from locations where it's not quite so warm. Maybe the wind we could do without. Personally, it's kind of hard to keep the hat on my head with the wind out there. So you know, my perspective here, I'm going to throw my perspective in for just a second. We had about 20 years of what I would consider to be organized markets, you know, moving past vertically integrated utilities where you can kind of plan generation, plan transmission at the same time. We've got about 20 years of organized markets to try to figure out transmission. Figure out how to do it, figure out how to get wire up in the sky. We had merchant generation was kind of an initial challenge, a little uncertainty in when the generation was going to be. Then we had variable generation, wind come along, and you know, predicting the wind and figuring out appropriate dispatches for the wind. This was something of a challenge from the perspective of how do we build transmission. Unit retirements was another way of kind of challenging our perspective of where the generation is going to be. So we've had these 20 years, but now we're in an era of rapid demand growth. And to me, it almost feels like the rapid demand growth is saying, yeah, guess what? Time is up. Have you learned your lessons? Do we know how to build transmission to get it planned? And it's kind of something to think about as we listen to these presentations. So, you know, today the presentations are going to run, kind of span the spectrum of transmission planning. We're going to start with Millstein with Berkeley Labs. He's going to be talking about valuing transmission. And we're going to have Ahmed Rashwan with Electric Power Engineers. He's going to talk about some of the barriers to transmission planning. And then we're going to have presentations from two of the regions that, you know, I really think have kind of figured it out. How to get transmission built, how to move forward with actionable planning. We have Wook Kang from ERCOT is going to be speaking, and then we're going to have Armando Figueroa-Acevedo with MISO, who's going to talk about MISO transmission planning process. So the question remains, though, are we ready? Please try to think about that as listening to the various presentations. And with that, I will turn it over to Deb. The floor is yours.
Okay. It's like I've got to use these areas here. All right, well, thanks so much for having me, everybody. I am Deb Millstein from Berkeley Labs. I'm going to talk about our analysis using recorded prices to gain insight into transmission value. Two objectives that we have here are, one, to just identify transmission value, and the second is to more about understanding the conditions that drive transmission value specifically. This is meant to complement sort of traditional forward-looking models that look at transmission value, not to replace them. Obviously, we have caveats and assumptions that our work is based on, and the important thing is that those assumptions and caveats are different from what are in the modeling set of caveats and assumptions. And so having sort of independent, different caveats going into something is very useful. So we can gain a lot of insight from looking at the historical price cycle. From a basic research perspective, beyond just identifying transmission value, we're hoping that some of the lessons or insights we gain here, so like looking at the key times that drive transmission value and what those conditions are, might provide information for modelers to check their assumptions and see if they're representing those particular drivers of transmission value. So for a good chunk of the presentation, I'm going to focus on this one metric, and it's a very simple metric from using market prices, LMP specifically, locational marginal prices, and we look at simply the difference in hourly price between one location and another. And so we look at that difference each individual hour, and then take the absolute value of that difference, and then look at that across the average of that difference across a long period of time. So it starts with sort of an instantaneous or hourly cap, like a single hour price difference, and then expands that over a long period of time. Because these are based on marginal prices, this is a marginal metric, and so with a whole bunch of important caveats, which I'll mention in a second, one way to think about this would be sort of a market signal for the value of the next unit of transmission between two locations. But of course, we have a number of simplifications here. We're assuming frictionless transfer of energy between those locations, and we're not accounting for alternating current flow complications, to mention a couple of the caveats, but there's others as well. We can calculate this value with day ahead or real time prices. And we do that to compare the results to each other. So one other important thing is that this is a subset of value. This is just a market signal of value. It does not include things directly like reliability or resource adequacy values, which might be looked at in some cases. Okay, so it's possible you've seen this figure before. This is newly updated through 2024 for this conference. And what you're seeing are 70 links or so across the US, at which we looked at the potential value of transmission, that transition value metric, which I just showed. And I'd like to just point out a couple aspects of this map. So one is, for many of these links, we have data from 2012 through 2024. So that's 13 years of data. That's quite a long record of empirical prices. And over that time, many of these links have an average price difference of $15 per megawatt hour or greater. So that's over 13 years of time. And that's a remarkable pricing difference between locations. So any of the darker oranges or red colors are at 15 or greater dollars per megawatt hour. So I'll make the case that that's a large value now, but later on I'll do a more detailed comparison of cost to put that value into context. So from this universe of links, we can ask a number of questions. So we'll sort of divide the questions into a few categories here. One is we'll look at where and when transmission is valuable, as indicated by this market signal. Then two, we'll look at what drives transmission value specifically. And then finally, we'll go beyond that marginal value metric and do a direct comparison to cost estimates. All right, so first question, where and when is transmission valuable? So let's look at the value over time here. This figure shows the median value each year from that set of 70 links I showed in the map. So this is sort of the middle value across our universe of links. And what we can see here is that, first of all, there's no trend in time. There's no evidence for like a continuous trend in time, but we do see a lot of variation. And that variability follows average electricity prices and natural gas prices. So you see 2022 as the highest value year for transmission, and that's also the highest average electricity prices. There is some regional variation, which gets picked up in average value. So if you look at the average across the 70 links, you see that there's a couple more years that are higher value here, and that has to do with sort of regionally limited conditions that occurred that year, which affect the average value across that universe of links, but not as much necessarily the median value. So the Median value follows average electricity prices, and average value can be affected by regional conditions. So that's an introduction to sort of a when question, but now we're going to think about a where question, or maybe this is sort of a selection question. So what links were the most valuable? And we see pretty clear results here. This is again from that universe of 70 links. And if we look at cross interconnect links, we see that their median value was $30 per megawatt hour, which is twice as valuable as our interregional link set. So this is links that cross ISO or system operator boundaries, but not interconnect. And then again, within ISO, the links we have are about half as valuable again as those interregional links. So both the interregional links and cross interconnect links are quite valuable, but the cross interconnect links are really valuable. And then this is sort of a subtle aspect of the where question. This is about directionality, and a question that often comes up with transmission is like, is this just going to be from a low price location to a high price location? And what we see here, if we look at our cross interconnect and interregional links, is that these links, these interregional links are more balanced on average than sort of within region links, and they're relatively balanced just in an absolute sense. So many of these links are derived value. So like a 0.6 on this figure means that 60% of the value comes when side A has higher prices, and 40% comes when side B has higher prices. So many of these links are pretty balanced here between each side having higher prices. In other words, that means you could potentially lower prices on both sides. Some of the within region links are also balanced, but many of the within region links are much more sort of unidirectional, areas of supply sort of being transmitted to areas of load. So it's a different process going on than what's happening with these interregional links in terms of what drives value. Okay, so I will summarize up those points in a minute, but first we're going to go through the what question. What drives high transmission value? So the first conclusion here we look at, which is just pretty simple to calculate that metric, the transmission value metric, with real-time prices and day-ahead prices. And we see across years there's quite a bit of variability, but the real-time value for transmission is about 1.3 to 1.6 higher, depending on the year, than the day-ahead value, with quite a bit of variability year to year. So a lot of the value in transmission value, according to that, is then driven by real-time variation. And of course, electricity prices on average are closer to parity between real-time and day-ahead. Real-time prices tend to be slightly lower than the day-ahead prices. Okay, another aspect of what drives transmission value is that it is highly concentrated in time. So here we're showing that about 50% or so of transmission value is derived from only 5% of the hours. And that's in the real-time market. Day-ahead market is a little more spread out, but still pretty concentrated with 40% of the value, top 5% of hours. So we have a value that's concentrated in the real-time market and concentrated in time. And now we can look at sort of the conditions that really drive those high value hours. So here I'm going to introduce a new concept. We are calling this unforeseen intraday variance. And basically how we define and how we're meeting this threshold is that on one side of a link, we see that the price has changed substantially from the day-ahead market to the real-time market. And so there's a limited hours that meet like a pretty strict threshold for an unforeseen intraday variance. And what we can see here in this left figure is that as you rank your hours across all the different times and locations, the hours with the highest value that are ranked the highest value are heavily associated with unforeseen intraday variance, and hours that don't have any unforeseen variance are sort of spread out across the rest of the ranking, but really dip down there at the end for the high value hours. So the highest value hours are really driven by unexpected things that occur between the day ahead and real-time market. So that's a key driver of transmission value. Now, we looked at some other drivers, and this is an area of ongoing research, so I'm going to show a partial answer to other drivers here. Okay, let me just give a little context for what this figure means. This gray bar on the left is sort of the full universe of the top 5% of hours or so. And then all the other bars show sort of conditions that overlap with those high value hours. And so this big blue bar, the second bar there, is the hours with that meet the unforeseen intraday variance threshold. And so it's a big chunk of time, of course, of the high value hours that's associated with that intraday variance. And that's similar to what I showed in the last slide. But then we looked at some other factors too, like high net load hours or cold weather hours or high renewable generation hours. And the key thing to notice here is that those bars are very small. In other words, that on their own, things like high net load or cold weather or high renewable conditions do not lead to these high value transmission conditions. But in combination with some sort of unexpected variance, then those conditions can lead to high value hours. And then finally, there's this chunk, the darkest blue chunk there of the unforeseen variance. It's not associated with those particular other drivers we looked at. And we have active research right now looking into things like load forecasting errors and outages as drivers of the rest of that potential high value hours. Okay, so far we have seen this where and when is transmission valuable, most valuable, and we saw that it's interregional links and especially cross interconnect links. We saw that over time, value varies annually with average prices and natural gas prices, but there's no particular evidence for a long-term upward trend, really. And one other note about the sort of where is that we saw these interregional links and cross interconnect links were pretty balanced in terms of which side drove the value. We saw that transmission value was heavily concentrated in time, so just 5% of hours accounted for a large portion of it. We saw that the high value periods were associated with this unforeseen intraday variance specifically, so and that a few other potential drivers were not strong drivers on their own, so high net load, cold weather, renewables rarely drove high transmission value periods on their own without something unexpected. Okay, so now we're going to move on to the last section at the top where we look beyond this marginal value metric and do sort of a scoping comparison to published cost estimates of a number of transmission projects. So in order to move beyond marginal value, we have to understand how there could be price convergence as you have transmission. So we can think of this as on the low price side, when you have transmission, you sort of march up a supply curve to a slightly higher price. And on the high price side, you similarly add transmission and march down the supply curve. So I won't be able to go into all the details of this, but we developed supply curves for each location here based on empirical pricing histories. And then that allows us to calculate how the marginal value of transmission declines as you install more and more of it. And the area under that curve is then the total value for, in this case, a gigawatt of transmission between two locations. One more detail, so the actual pricing data is quite noisy. Many of the hours fit quite nicely to fitted supply curve that we developed, but there's also a number of hours that are outliers, and we had to treat those with that bounding approach, where we used a pretty conservative, for the low value bound, we assumed an extremely steep supply curve for those outliers. In other words, they lose value quickly. So with that, the lower part of these bars represent our low bound estimate for the outliers. We can look at across our universe of links, how much lower the total value is after a gigawatt of connection compared to its original marginal value. And we see about a 20% decline across this set of links. Obviously, there's some are more and some are less, but that's sort of an average. And so that's a useful finding right there to show that sort of price convergence wouldn't necessarily erase these types of marginal value signals that we see. Now, we then took the next step of looking at a whole bunch of published cost estimates of transmission projects, and some of these were retrospective, looking at costs after something was built, and some of these are prospective, so it is a variety of types of cost estimates. And then we looked at the total value, so including that price convergence, but this time often going past the gigawatt to match what was studied in the cost studies. And we see some important findings here. Number one, if we look at the cross interconnect value, just from the energy market signal, we see that the value estimates there are much larger than the cost estimates. So that indicates that there's potential value to pay for this infrastructure. In the interregional set, so now not cross interconnect, but cross system operator region, we see similar but a little bit muted. So some of the costs and value estimates overlap, but some of them are still quite a bit larger. And within region, value estimates are, some of them are lower than the cost and some of them are higher. All right, so I will conclude here. Many transmission links have significant values. This is the identifying value piece. And so as indicated by market prices, there's potential, there's quite a lot of potential value there. And that's not just the marginal value, but at least after attempting to account for price convergence as you add infrastructure. We really focus on the interregional links and the cross interconnect links as especially valuable. And when we compare those interregional and cross interconnect links to cost estimates, that really sort of provides some context for the value signal for the market, and that it's much larger than the cost estimates for those cross interconnect links. Now, hopefully you also have a lot of questions from this work. We certainly do, and so we're doing a bunch of follow-on research to try to answer some of the questions that have arisen for us. We're looking more deeply into this unforeseen intraday variance and what specific aspects drive the unexpected changes between the day-ahead and real-time market and how that then might affect transmission value. We're improving our empirical techniques to estimate supply curves. We're looking at links between electricity system modeling, and if you can bring in these specific conditions we've identified in the empirical pricing record. And another thing we're looking at is how actual flows occur and whether those are efficient. And so I will end there. Thanks to DOE for the funding.
Okay, on, you are up. Please, thank you.
Okay, good afternoon, everyone. I'm excited to talk to you all about integrating transmission silos today. I'm Ahmed Rashwan. I'm the Senior Director of Transmission Planning and Operations at UP. I have the privilege of supporting utilities from coast to coast with their transmission planning work, really getting a perspective on how different areas approach similar problems. So before we dive into it, let's characterize what a transmission silo is. And today, generally, our practices are all within a transmission silo. So when you think of generation interconnection studies, TPL studies, long-term planning studies, transmission service requests, deregistration, they're all done within their own set of assumptions, their own dedicated teams, their own groups. And so what we're finding is there's a lot of recommendations for system enhancements that come out of various silo processes, but certainly can have overlap on the systems that they are actually recommending upgrades to. So ultimately what we're trying to drive towards is a more integrated approach to determining what requirements we should be putting out there for new facilities. And so we talked a little bit about how the system is changing. So, generally I try to ground myself in the purpose of transmission planning, and then it's really to identify the investments needed to ensure that operations can succeed in its ability to deliver reliable power. So we always have to ground ourselves in that. It's not an arithmetic exercise or a hypothetical exercise done without that in mind. It really is to enable operations. And so the processes that we have today have proven adequate, I think, for the decades for which they were established, where there was incremental changes happening on the system. And those silo types of approaches were functional in that type of incremental change environment. But now we're seeing a large change in that, and we're seeing magnitude and pace of change increase significantly. And so what this has led to is infrastructure has been trailing needs of the system. And, we've seen over 20 billion in congestion in 2023 alone. And so we feel that, with the changes that we see on the horizon, right now really is an opportune time to start thinking about implementing more integrated planning processes, where we're really focused not on individual needs, but multiple need planning. So when you're looking at planning, you think of what are my needs across different spectrums, be it policy, be it reliability, economics, regulatory, and consolidate those together when you're considering developing plans. And when you put those together, you'll end up with a more optimized portfolio. So getting much more bang for buck on the money that you're spending. So let's think of some of the drivers for the changes that we just talked about. So on the generation fleet side, generation deactivations of coal and gas continue. As you can see on the diagram on the left. And there's definitely an increase in renewable generation and storage as their market share increases. And so with this, the operating characteristics of the grid change. Less centralized, very controllable devices from the grid's perspective to decentralized, energy limited resources that even combined with storage, you still really have to optimize to get the best value from them. On the load side, and thank you for the grid strategies team for allowing us to use this. I think it was a really good chart. We're looking at adding 128 gigawatts of load between now and 2029. That is exceptional. And not only in size, but again, also in pace. And we all know a big part of this comes with large loads, onshoring of manufacture, chip fabrication, electrification, driving all of these. And so that's definitely a driver for change in our processes. When we continue to look ahead into different drivers, resilience has become a bigger focus in the system than it did before. We're seeing that there's a lot of a higher frequency of disaster events. Per the data shown on the left from the US $1 billion disaster events since 1980 up to 2024, as the continuum of time progresses, the amount of storm-related events, for example, have significantly increased. So the challenges of maintaining reliability have now shifted to also being able to manage these, what were previously 1 in 20, 1 in 30, 1 in 40 year events, becoming 1 in every 5-year events, 1 in every 3-year events. So how do we plan the system to withstand that? Because we do want to maintain the same level of reliability that we have today, if not enhance it. When you start to think of operability, not something we generally consider in the planning timeframe, but something we definitely need to start considering now. These are two diagrams from ERCOT's 2024 LLTF presentation at ERC and the October 2024 presentation. The one at the top shows the amount of large load loss or reduction events. These are all for out of zone faults. So this load was not lost by configuration. These loads just tripped off because voltage dipped to a point where these are very sensitive facilities and they were knocked off. So when we're designing a power system, traditionally, this was not something that we were considering. Now it's certainly something we need to pay attention to because these losses can actually cause downstream impacts. It can cause cascading outages. So definitely an area of focus. And also when you think of operations, balancing is very important. When you look at the bottom curve from October 2024, what this is showing is that regulation capability in ERCOT, just from the variability of loads, and that's the amount of load that they had at the time, not the amount where we're going. The regulation capability was fully accounted for just by the variation of large loads, nothing else. And so we're seeing additional pressures on some of these ancillary services that we need to provide to ensure reliability. And so these are some things that, if we can analyze them ahead of time and the planning time frame, considering operability, they'll certainly help us achieve better outcomes in the future. And so let's look at how investment has looked for the past while. So leveraging FERC Form 1 data, and I don't know if anyone has ever tried to go through FERC Form 1 data, but it's definitely a challenge. But we're able to consolidate it onto a single diagram. And I guess my takeaway from this is, since the 2010s, we've been around $25 billion to $30 billion a year of investment. So quite a bit of investment on a yearly basis. My expectation is with the changes that we're seeing, these numbers are definitely going to increase. We need to add facilities to serve load, to supply generation, and generally for every megawatt of load that you're supplying, there's a multiple for generation that you need to connect. So definitely expect this to increase. And so if we take a deep dive into 2023's allotment, a huge amount of this is focused solely on base reliability, or what we have here as, sponsored upgrades, which generally, I think in this case, the bulk of it represents like-for-like transmission replacement. So almost half of the expenditures in 2023 were on like-for-like replacement, which are not actually subject to any analyses. It's more, I want to maintain my rate base. And there are opportunities there to say, well, these facilities were required maybe 30, 40, 50 years ago to serve a purpose. Do they continue to serve that purpose? Are these good investments for us to make? But as of today, those are kind of a siloed process where you look to just replace your rate base. And then you look into you continue the continuum from there on. Multi-value didn't necessarily show up in 2023's actual build, but economic did, as well as generation interconnection. So again, very siloed for how things went in 2023, focused largely on reliability and like-for-like replacements. And so what are some of the drivers for transmission silos? So alignment of timelines and study horizons can certainly be challenging. How do you make this work in a more coordinated fashion? And with more unknowns in today's planning processes, the further you look out, it does become more challenging. So silos are a way of controlling those unknowns by just fixing them. And given the pressures in the industry today, everyone wants to connect yesterday. And so by doing things in a very siloed fashion, you can try to expedite that by just looking at the problem at hand, not looking at it more holistically. When you think of cost allocation, when you're doing generation interconnection projects, you assign costs to the generators. When you're doing large loads, you're assigning costs to the loads. If you start to put this together, what's the share for each? So cost allocation becomes a little bit of a challenge on how do you allocate costs appropriately to the impacts that are being caused by those facilities. And that's very much an art, it's not a science. And I don't know if anyone from the SPP team is here today, but they're going through the consolidated planning process right now. And this is definitely a point of discussion that's been coming up. Jurisdictional boundaries, you focus on your area, your territory. And there are some states that are multiple territory from an ISO RTO perspective. So every planning territory is focused on itself. In very seldom cases are there real coordination between different ISOs or different jurisdictions. And lastly, I think this is a really interesting one. So transmission planning teams are normally separated by function. And really simply think of GI and think of planning. And then they're further separated into who does steady state, who does short circuit, who does transient stability, who does EMT studies. And so everyone is functioning in their silos. And a lot of the communication that you would hope that would happen to arrive at a more coordinated set of solutions, unfortunately becomes very hard when you're fragmented into that level in organizations. And so let's take a look at some of the recent investments that we've seen. And I think I do want to commend MISO on LRTP, and I know they won an award for it yesterday. So significant investment there, and a lot of this actually is multi-need. So they do look at policy, economics, they look at reliability and enabling generation interconnections. So a lot of multi-need planning happened in that instance. SPP's recently released a 7.7 billion portfolio, including 765, which is really encouraging for that transmission backbone. We talked a little bit about it regional a moment ago. MISO and SPP have come up with a really good process for JTIQ to help address issues on those seams between their jurisdictions. PGM's recently done a $5 million portfolio for RTEP window 3. And we're in Texas. ERCOT has previously announced a 13 to 15.5 billion Permian Basin plan. I think we'll find out next month what voltage level that is. I'm cheering for 765. Hopefully we can get that. And California's also had large transmission portfolio, the 6.1 billion last year, and New York's recent Long Island public policy transmission portfolio has been around 3 billion. So lots of expenditures happening. Because MISO has great data, and I thank you, MISO team, for publishing this, we're going to take a little bit of a deeper dive into what they've historically been improving over the past few years. So if we look at MTEP 2023, it's largely driven by, and the other category here is the like-for-like replacements amongst a few others. There's been a significant amount that's been like-for-like replacements, reliability, and some generation interconnection. When you look at MTEP 24, that includes a $21 billion portfolio for LRTP Tranche 2. You get a huge amount of multi-value plan. And then now we're looking at what MTEP 2025 is based on the data that we have today. I wasn't able to get the voltage levels for it, but we definitely have the breakdown. Again, we're coming back to more of that like-for-like replacement and more solid approach. And so what we're seeing here is definitely an opportunity to leverage the learnings from LRTP, the approaches developed in LRTP, and have those applied more universally than on these exception-based studies where you're looking at kind of a regional backbone. And I think the diagram to the left that talks about voltage reinforces that LRTP was focused on the backbone, with a huge chunk of the cost being related to 765, 500 kV, as well as 345 kV upgrades. If we can make this more a regular process, I think we'll start to see some of those benefits come through. And so what does integration of processes mean? We've talked about the challenges with being siloed. So how can we integrate processes? And so we're going to talk about a few different approaches here. Initially talking about integration of processes, expanding the breadth of what we consider, and then the depth of what we consider as well. So integration of processes, you can do a wide range of things, varying from integrating between different processes that exist, or integrating the actual processes together. So there's a spectrum that exists between those two kind of bookends. Generation expansion planning integration is a great way to align generation interconnection, where there's a lot of upgrades being tabled to facilitate generation integration with long-term planning. So if you perform a generation expansion plan looking at likely locations for future generation, that will help align some of your planning assumptions with what can likely happen in reality through a generation interconnection queue where you have those unknowns today. We think a really powerful way of approaching efficiency for upgrades includes consolidating and optimizing your upgrades and even the needs side of things. Different ways to approach this is to look at your needs as a bucket and how you can tackle those together. And that includes reliability analyses, economic analyses, policy, GI. You can look at them holistically and say, what am I looking to address here? And then recommend a portfolio to support that. Or you can also look at upgrades that were resulting from those individualized processes and say, where is there overlap? How can I upgrade? How can I optimize these processes? So different approaches either from the need or from the actual outcomes of those processes. In near-term and long-term plan continuity, this is becoming really important because some of the issues that we're trying to tackle today require definitely longer-term investment than what you can do in the near-term time frame. So ensuring there's alignment between the two, and maybe a really simplistic example could be if you are building a new transmission and in the near term you only need one line, but in the long term you need two lines. It makes sense to build a double circuit tower, hang one circuit on one side, and then in the future give yourself that optionality to add the other circuit. I know it's a very simplistic example, but it is trying to illustrate that you need that continuity between the two so that they're coherent and not, conflicting with each other. Expanding breadth of planning. So certainly policy is really important. I think a really simplistic example here as well is if you delay considering something like notices of retirement. So when you start to consider retirements in your planning processes, it's too late. Those generally happen a year or 2 years ahead of time. If you had the ability to incorporate retirements into your long-term planning assumptions, you'd be able to better account for those and come up with more effective upgrades to address them along with the rest of your portfolio. Interregional continues to be an area of opportunity. I think there are some challenges that we have with how to value interregional, how to make sure it's there when you need it. But those are things that we can tackle as an industry together. There are tons of areas that are overgenerated and areas that are undergenerated. And so in concept, there are opportunities to connect those together. California has a really good process today where they accept applications in, and on a biannual basis, they'll initially look at the projects and review them. In the second year of that biannual process, they'll actually study them as part of their solution portfolio. And so we've seen SunZia as an example come through that process. We talked about end-of-life assessments. Maybe starting to consider those as part of your planning portfolio and saying, well, if I don't have these facilities, I take them out, what issues come up and how can I address those? We do want to acknowledge that there is a natural, I'd say, a challenge that comes with this because there's a disincentive for utilities in some cases to do this because they want to maintain their rate base. And if they take facilities out of the end-of-life pool, that could put it into the competitive windows, and that itself is a disincentive. So finding ways to ensure that utilities are incentivized to consider end-of-life portfolios if they're still needed going forward. Increasing depth of planning. So we talked about uncertainties potentially driving silo behaviors. And I know FERC 1920 has talked about scenario-based planning being required. This is a really good way to establish a spectrum of potential futures and trying to identify portfolios that can support those to the best effect possible. And so this is, again, a little bit of an art, but the idea here is to really understand when you vary some of these assumptions, what do those futures start to look like? Are there better upgrades that you can make that can satisfy a lot of those futures relative to certain ones that we'd only identify today with a deterministic model? And multi-value project evaluation is also a way to help. In some cases, if you look at something and you understand its value, let's say just from a reliability perspective, and when you start to stack on other benefits like policy enablement, economic benefits of that transmission, those can help justify the case to build that transmission. And increasing depth of planning. So like I mentioned earlier, we certainly have a lot of large scale changes that are happening today, and both on the supply and demand side, and they are certainly stretching our existing processes, which were designed on the incremental changes. And so what we're looking here is to find ways to better understand the characteristics of these changes. So large loads, for example, we talked about some interesting behaviors that were there. Establish the appropriate technical processes that you need to integrate these. So an example we didn't talk about at this point might be some of these large hyperscalers. They can move load in and out of any jurisdiction, depending on potential economic reasons or variable generation potentially being on the margin, and they're trying to maintain a green footprint for their facilities. And so they can move it from one jurisdiction to another based on any set of requirements. So if you're sitting in a jurisdiction that has, let's call it 5,000 megawatts of hyperscale load, how much of that can disappear based on strictly economics or marginal fuel? they could move into another jurisdiction. We don't model those events in planning. We don't model losing. Jeez. We do not model losing 3,000 megawatts, for example, of load just like that because of price in a different jurisdiction. It's not a P1 or a P2 or a P3. So we start to think about that. What do we need to adapt in our processes? So we have to increase our depth in planning. I'm going to try not to hit this again. I'm sorry. And you know, the additional operational challenges, and I think it's great that Deb touched on this because there are a lot of operational uncertainties that didn't exist before. Now you have operational uncertainties on your generation side and your load side. Those need to be factored into planning so you can appropriately plan for them. You know, flexibility came out of the fact that your generation fleet became less predictable. You're probably going to need more flexibility on the system now that the load is. How much flexibility do you need? How do you quantify that need? And that needs to happen in planning. It can't happen in operations planning. It's too late at that point. You know, we talked about resiliency. You know, there's been a lot of discussion on resiliency from a resource adequacy perspective. I have 50 seconds left, so I'm going to try to go through this quickly. It's important to minimize impacts. Look at supply and path redundancy. But I think it's also really important for us to consider that we can't prepare for every single event. There are going to be system losses. The discussion should also start to incorporate things like restoration plans that are detailed and nimble and enabled by some investment. So if you're going to be putting on circuit switchers, you're going to be putting in grid forming inverters, more black start needs on in your jurisdiction. Those are some things that you can have that can help a timely restoration following some of these events. So these are some things we're also thinking from a depth perspective to include in these planning processes. Really quickly, work structures. I think we can do some work there to get them more closely aligned so that we have consistent outcomes. In data sets, I mentioned, you know, we have MISO having a great data set for us to look into. Having data to help us evaluate how effective we've been in putting together these transmission portfolios would really help us drive into different directions where we're more integrated. And so I just wanted to share potentially two bookends of what, you know, integrated planning could look like. So integration between processes, as we mentioned, you can take inputs that are really those integration between processes. So end of life assets, GI, load growth, policy drivers, and continue to do your studies in a siloed way. Look at reliability, look at economics, look at policy, and in the end, consolidate your upgrades. Then you merge that with your long-term planning and your interregional opportunities, see if there are opportunities to further refine that upgrade consolidation, and then you end up with a multi-value and multi-need transmission plan. That's one approach. A different approach, and this is more aligned with what SPP is trying to do with the CPP, is take your inputs, but integrate the analyses together, coordinate them together, so that they're looking at one starting case, and there's a continuum from there on. So there's one set of assumptions that you're working with that go the rest of the way. So you have the same starting point, consistent conclusions. Then you go ahead and you can either upgrade that with the needs, you can do a consolidation from that, or you can do an optimization, and then you end up with a multi-need, multi-value transmission plan. So again, takeaway could be integration between processes and integration of processes and anything in between. And so that was my presentation. So thank you for your attention.
Okay. My name is Kang from ERCOT. As you know, a lot of businesses and coming to the Texas state, we see a lot of population growth and economic developments. And ERCOT receive a number of load interconnection and generation interconnection requests on a daily basis. So today I'm going to talk about some of the key challenges that we have and what it is options and opportunity to shape the future of ERCOT here. For the sake of the time, I will skip this slide but we can come back later if you have a question of that. It's about the ERCOT system. So what really triggered all the discussions, right, around, the major, infrastructures and evaluation of various options. For the most part, it all started from the oil and gas business developments in the Far West Texas region. It's a home of Permian Basin, and the Permian Basin is one of the world's vast prolific oil-producing regions. And that region is experiencing, significant load growth, right? And partly because of the new oil and gas drillings in that region, and also associated with business developments, and also because of the electrifications, conversion of existing gas and oil operations from self-generations to the transmission connections, right? I believe they try to convert the services to transmission because they want some, better and reliable electric services. But providing them a transmission services has been so challenging, particularly in a timely manner. It's been so difficult. And mainly because, as you can see in the map, there's not much infrastructure for West Texas region. And second, when they planners need a long-term load forecast to come up with appropriate, long-term transmission solutions. But it's been so difficult to get the long-term load forecast, the long-term load commitment from the load customers in the past. I heard that it's mainly because of the nature of their businesses. A lot of their long-term business decisions are affected by many different factors. Federal policies and actions taken by other oil-producing countries, fluctuations in the oil and gas prices. But when they come to transmission, they want the connections within 1 to 2 years. So aggressive schedule, right? But as you can see in the flow chart, it typically takes 4 to 6 years to build a new transmission line on a new right of way in the ERCOT. I know it's relatively quicker than other interconnections and other regions of the US, but that's where we have fundamental difference and challenges coming from that difference between their side planning and our side, our side transmission planning. But regardless of the challenges, ERCOT and our stakeholders has taken significant steps to address all those issues and accommodate huge load growth there. As you can see in the time chart, we did a bunch of studies. It goes back to 2013, but I started in 2019, 2021. We proposed billions of dollars transmission projects. Many of them are under construction. We also, work with our university partner to better understand the long-term load forecast associated with that, oil and gas fields in the Far West Texas region. And Texas lawmaker in 2023 passed House Bill 5066, and that House Bill 5066 ordered ERCOT to conduct the Permian Basin study one more time. But this time, all load, right? Not just community load, but also load sponsored by the TSP, transmission service providers, and also the load that's verified by the third-party, consulting companies. So we did that Permian Basin studies, but it's not just Permian Basin issue. It happens everywhere in ERCOT. A load pops up everywhere in the current connection. So we did conduct a system-wide reliability studies during the 2024 annual planning assessment process, which is called regional transmission plan process. And as an outcome, we came up, we published a transmission expansion, comparison white paper. I will talk about that a little more, but we all these documents are available in the ERCOT website. If you want to know more details, you can go to the website and find the details here. This is a high-level process that we adopted to develop this, major transmission plan. Okay, we started with a communication study. We reviewed, we assessed, considered various options, and came up with this 345 and 765 kV option to provide, major input paths, new input paths to communication region to serve that huge load growth in the area. And all that options, approved by the PUCT last year, except the most 11. They are going to make a decision sometime in April or May, I believe. Okay. But as I mentioned, we need also, look at the entire network to come up with the holistic solutions. As I mentioned, the loads come up, load growth happens everywhere within the ERCOT grid. So in 2024, annual planning assessment, we did a system-wide study using on top of what we found in the communication plan study, okay, to come up with ultimate 345 and 765 kV options for the entire ERCOT network. Okay. The transmission expansion plan comparison white paper, it outlines the cost and benefits, okay, compare those performance between the two options. A lot of good details, good information there, and you share with the PUCT, that PUCT, can make informed decisions, by reviewing that white paper as well, right? So what are we talking in terms of demand, right? As you can see in the table there, the study that we did last year, based on the House Bill 5066, we assumed about the 23.6 gigawatts, right? We did the same study back in 2021, okay? The same year, same area, we assumed the 10.5 gigawatts. It's almost, more than double, and it's almost like 124% increase in the communication regions compared to the previous study. So, half of that load, about 11.9 gigawatts out of 23.6 gigawatts is coming from, oil and gas business, and the other half is coming from different business sector, like data center, crypto mining load, hydrogen productions, and other, commercial. For the system-wide reliability assessment, annual planning assessment, we assumed about 150 gigawatts, right, for the entire network. I looked at the previous assessment in 2023. We assumed about 110 gigawatts, so almost 40 gigawatts increase. It's huge, huge jump. And as you can see in the map there, the load growth happens everywhere, but many of them are concentrated in and around the major load center, Dallas, Fort Worth, San Antonio, and Austin, Gulf of Mexico region, and also Coast West Texas region. That brings up one of the challenges, because it not only requires the major upgrade for the local network, but also requires major transmission highways, right? Connecting, generation sources to the major load center. I also looked at some numbers, historical peak, that we set in 2023, it was 86 gigawatt. If we add that 150 megawatts, gigawatts appear in the 2030, that's going to be an 8% annual average growth. So that's going to be a huge sorry. Speaking of the load, we have a load interconnection process. Currently, in our process, in our queue, we have more than 63 gigawatts of load. And they're coming as different types, different sizes. Some of them are really, crypto mining and data center. some individual load is a gigawatts, 2 gigawatts, okay? That brings up another challenges and concern around, potential frequency instability issues. As I mentioned, many of the large amount of, that data center loads and large amount are concentrated in one region. They triple together during some, unexpected real-time fault events. That's gonna, that may, cause some, frequency fluctuations. Okay, so that's another challenges that we see here. As far as generation assumptions, we assumed a huge amount of load in the study. So we also, modeled a lot of generation. Many of them are coming from the generation and connection queue. And about 11 gigawatts was also some generations that not in the queue, right? It was necessary to address the generation shortfall, right, in the study cases. And as you can see in the map, some of them are located in the brown side where we have generations already retired. That's going to be a good location. And others are located in the regions where we have major infrastructures already under constructions or approved by the board of directors. So it's a lot of assumptions and challenges in what's load and generation. And as far as generations, we currently have about more than 380 gigawatts of generation projects in the queue. As you can see in the chart here, more than 90% of them are IPRs, right? Solar, battery, and wind. I mean, as you know, IPRs are different. They basically rely on the strengths of the grid, right? So more and more IPRs, lack of online conventional generation sources, on a limited transmission infrastructure. I mean, our system is going to be weaker and weaker, right? And that brings up another, potential, concerns around, increasing system instability issues during the, unexpected, real-time events like Odessa that we had back in 2021. So with that all considered, we try to consider all those, challenges as much as possible and came up with this 2 major infrastructure plan, right? The green dotted line on the left and the orange dotted line on the right are basically the same as the permutation 345 and the 765 kV plan. And the purple dotted line on the right, that's basically the extension of the permutation 765 kV plan to connect, to serve the rest of the grid and to connect all the, load and generation resources. Right? The dark gray line, and it's basically, new 345 kV line upgrade or the upgrade of existing transmission, 345 kV transmission facility. But as you can see in the map, 765 kV plan provides a lot less 345 kV upgrade, right, compared to 345 kV plan. Okay. I just want to mention the 2 things here. The first time that I heard that the first time we got access, 345 kV together was back in 1960s. So it's been more than 6 years. That it looks like we need to think about the next step, right? And 765 kV technology is not new. It's been out there for many years, right? And it's available in other countries or other parts of the US, but it's simply new to ERCOT. I know there's some concern, but we will address that with our stakeholders if PUCT approves that option. In summary, 765 kV plan that we have require 12 new substations, and each substation will need 2 or more transformers Again, the line of grade mileage is about 2,800 miles, and it's a lot shorter than the 4,174 miles in the 345 kV plan. This is the summary of the cost and benefit comparison for the two options. And all this detail, a lot more details are available in our transmission expansion plan comparison white paper. I don't plan to go through these numbers, but what I want to say is that we did consider publicly that, right, in terms of mileages of new transmission circuit, in terms of mileages required for the existing line upgrade. And we also compared the baseline construction cost, $30 billion compared to $32 billion. Okay. 345 kV projects is a little more cheaper, but that cost together could be reduced if we consider many other different aspects. For example, some of the existing line, some of the lines that need to be upgraded, going through the major major load center, heavily and densely populated and commercialized region. The crew may not even be able to take some construction out the window, right? It means that they need to take some different approach, such as energized constructions. So upgrade the line while the line, while that line is energized or hot. So that will add more complexities and cost to the overall picture here. So we expect that some of the baseline the cost again is going to be reduced further down. We also looked at the 8760 production cost simulations and run the economic analysis to see understand what kind of benefits each options provide. Appears to be that the 765 kV options provide a lot more savings in terms of production cost and also savings, energy savings for the consumers. In addition to that, we also ran a system loss analysis, right? And run a bunch of additional reliability analysis, transport capability analysis to understand which options provide additional flexibility in transporting power from across various regions in ERCOT. We did a dynamic stability studies to understand the impact or influence of the existing stability related constraint on the major transmission interfaces in ERCOT. We also did a bunch of sensitivity analysis to make sure that the plan that we have is good for the system, and the system should be able to handle any uncertainty that may comes in the future, right? That should be adaptable, flexible, and should be resilient, right? So we did a bunch of sensitivity analysis. We also, conducted a system strength analysis to understand, how each options improve the system strength. So all the details you can find in the ERCOT white paper, but this is just a summary of that. This is my last slide. I talked about the challenges. It's not just about the goal, right? It's about the generations and transmission constraint. And ERCOT market is different compared to other, MISO markets or PJM markets. We have a lot of challenges, but according to our study result, 765 kV options appears to be the better options compared to 345 kV option. It seems to be providing a lot more flexibility and a lot more options for signing new generations and a lot more capacity and so on and so forth. So we're still waiting for PUCT decisions on the voltage level, but regardless, we continue to work with our stakeholders to make our system more resilient and stronger, right? That's all.
You're not. Okay. Thank you so much.
Right, well, good afternoon. My name is Armando Figueroa. I'm with the strategic assessments team at MISO, senior engineer. I'm going to talk about probabilistic methods applied to the long-range transmission planning process, in particular the business case. We've heard a lot about LRTP, MISO's LRTP in the EC workshop overall. So I'm gonna go into the details of how we did it and share with you all our experience with our stakeholders, the methods, how we develop those portfolios, how we calibrate them, and how we at the end how they got approved. So I'm going to go through all that process and focus on a few of the metrics that I think are very important and relevant to the panel, and pose a question at the end of how can we extend this methods that we are using in LRTP and MISO to other processes. So a little bit of key MISO facts for the ones of you that are not very familiar with MISO. One of the RTOs in the continental US, serve 15 states, cover our footprint in 15 states, including one Canadian province, more than 45 million people, have more than 500 market participants as well. We like to call ourselves the coast-to-coast RTO, from the Gulf Coast all the way to Lake Superior in Michigan. So we applied probabilistic methods in several parts of the organization, system planning, markets and operations, and also the strategy part of the organization. Probably all be familiar with the planning zone margin study, right? It's done at the utility level, but also at the RTO level. That's a probabilistic assessment, but it's what we call copper cheat. So we neglect transmission. Transmission gets included after the fact, but in the core modeling of our what we call the LOLE analysis of loss of load expectation, we neglect transmission. And that has been the tradition. So one of the key motivations for this use of probabilistic methods was to incorporate transmission in that assessment so that we can measure the value of a transmission portfolio by applying probabilistic methods. So you're going to see that connection between resource adequacy and transmission planning in this presentation, and that's going to be the focus of my presentation. This table is a little bit busy, but it includes all the benefits that we developed at MISO. This is a process that is integrated with our stakeholders. It takes a few years. It's very iterative, and we calibrate. So it's not only MISO doing the job, it's also working with our stakeholders. And these are the 9 benefits that we developed as part of the Tranche 1 and Tranche 2.1 projects. We leverage information from the reports that EC reports out from the working groups and task forces. So one of the ones that we reference a lot in our study, our methodologies, is the multi-value transmission planning for a clean energy future. So that's one that we use heavily in our methods. But more importantly is that integration of resource adequacy and transmission. If you look at this table here, the last 2 that I'm here that are kind of say highlighted, this rectangle, are the ones that apply probabilistic methods. So those are the 2 that I'm going to focus on in this presentation. So what do we mean by integrated planning in the context of the business case analysis for the tranches, for transmission tranches? The left side here, you see what the traditional resource adequacy model is. So it's an unconstrained, it does capture generation outages, right, based on mechanical failure. Also correlated outages. We have what we'll call the common mode type of failure, right? If you have a lot of units, thermal units in one side that are all connected to the same pipe, they might fail, right? The pipes might get frozen, etc. So we see those correlations in the historical information. So we captured that in our resource adequacy model. There's also load uncertainty, right? So load changes weather year to weather year. So that's another uncertainty that we capture in our resource adequacy process. Transmission is not part of that. It's we call it resource adequacy, right? Because it's resource focused or oriented. So what we did in LRTP was to say, hey, we have this process that we all agree on, we like. It incorporates uncertainty and it captures all these uncertainties. So why don't we extend this concept by applying transmission? And it doesn't have to be a full-blown nodal transmission model. It can be a simplified version just to at least capture those effects of transmission in the system by including also the uncertainties related to generation availability, to load, the different effects of weather. So in that second, the right side, that check mark should be included in that one as well. The transmission side, so we included that in the LRTP model that we developed for this tranche 2 portfolio. So I'm going to go into the details here, a couple slides. I'm going to flesh it out a little bit. So bear with me here. We're then going to look at the numbers and the why we think is a good approach that we can extend to our processes. So this is how we get to model. So we have what we call pipes and bubble model. So we neglect impedances. It's only a capacity based model, both from a generation and transmission point of view. Those links and those arrows that you see between the LRCs or the local resource zones and MISO and the MISO hubs are the local capacity import and export limits. So that comes from a transfer analysis that we perform offline, and that information gets used as an input in this model. So we have a MISO hub, and those transfers occur through the MISO hub. So by applying this concept, we can measure what those power flows are, right, from a region to region perspective. We also have a bubble that we call the external bubble to recognize transfer and imports from SPP, PJM, TVA, and the rest of the tier 1 neighbors in MISO. So how do we measure the value, the resource adequacy value of transmission? So the left side pipes and bubble model that you see here, it's a copy of the one that I shared in the previous slide. The one on the right shows those called orange arrows that are a little bit bigger, right? So it represents that additional transfer capacity that we're adding to the system with this tranche 2.1 projects. So it's a benefit, right? You can see it from the image. When one region doesn't have enough capacity or available capacity to meet demand at any time of the year, another region can support it, right? But if that region that has enough capacity is transmission limited, we end up in the same situation, right? There's no value there. So we recognize that transmission or those transfer limits and then increase them as a function of the portfolio, and then we measure the difference between those two cases. So a little bit of math here. This is one of the metrics where we apply the probabilistic methods. It's called the avoided capacity cost benefit, which is very similar to the one that was defined in the EC report. The question that we ask ourselves here is how much firm capacity can the portfolio avoid? And we do this by measuring planning reserve margin in a case that includes LRTP and a case that doesn't. So when you have additional capacity in the system, you have more availability, right, from a topology point of view to move power around when needed, from the places that have enough to the places that don't have. So measure that difference in PRMR when we include it, when we remove that benefit, and that's what we call the avoided capacity cost benefit. We take that number and we run an incremental expansion to figure out what's the economic value of that megawatt amount that is the difference between those two cases. So we run a full 20-year out resource forecasting expansion and the resource forecasting expansion figures out what's the optimal mix of that firm capacity and then calculate NPV, and that's how we get the value. So this is a summary of the benefits from a billions of dollar point of view. I'm focusing on this one because this is the largest chunk of benefits in the tranche two projects. So when we talk about this benefit to cost ratio, this is one of the metrics that drive that benefit, those benefits in the tranche two portfolios. We see a range here of those benefits. So the second one is focuses on tail events. The previous one, it's more what we call average conditions, still probabilistic and captures uncertainty, but it's based on an average metric, which is the loss of load expectation, right? So it's an expected number, an average across thousands of simulations. So here we look at the tails, at the very worst events that we see in our simulations, and then we measure the value of transmission, in this case, the tranche two portfolio, with respect to a case that doesn't have the tranche two portfolio. It's a very similar methodology that we followed for the avoided capacity cost, but here we are focusing only on those tail events. The challenge of this metric is that we need to define what's the probability of those events happening, right? So we again, this was a process with our stakeholders and vetted through workshops and meetings. And at the end of the day, what we did was we took the data and we plotted events as a function of conserved energy and duration, and we saw a cluster in the tail. So we saw events that were very large in magnitude and duration as well. And we said, okay, this is going to be our extreme or outlier in our data. And we have to make a decision of right to draw the line and say, this is from here to here, it's extreme, from here to here, it's not. So we did that in a scientific way, we think, and measure that threshold that we end up using to quantify benefits of transmission with or without the tranche two. So this is a table kind of summarizes all that that I just spoke about. It's a contour map or a contour table that shows in one of the rows, the columns here are weather years. So starting from 2007 all the way to 2021. The rows are the cases. So the top one is the case without tranche two, and the bottom one is the case with tranche two. So the colors represent the severity of the event. So the red represents the high severity. So these are voluntary and involuntary load shedding events measured using expected conserved energy. So it's the average conserved energy for that particular weather year. And then the bottom one is the one once we include the transmission topology, how much that severity of the extreme events reduce. And the difference between those two is the benefit of transmission, of the transmission portfolio for this particular benefit. So we also included we have a few meteorologists at MISO, spoke with them to try to correlate weather events that have happened in the history, polar vortex, the 2021, the 2019, the 2014. So I was an intern at MISO, but very first internship during that time, and was coming from Puerto Rico and into the polar vortex, -10 degrees. It was a big shock for me. So I remember that 2014. We wanted to correlate those weather events with the extreme events that we saw in the data and highlight the benefits of the tranche two portfolio with respect to that case that didn't include the tranche two portfolio. So these are summary of numbers of value. They're in the millions of dollars, high end, they're in the billions. It's a small part of the full benefit in the tranche portfolio, but still significant. And we're continuously evaluating better way to improve this methodology. So when we combine all the pieces together, all the 9 benefits that I talked about at the beginning of the presentation, this is the end result. This is the outcome of the whole process. We saw benefits on the lowest end of the spectrum, 1.9, at the very top, the range 3.8. So it's a robust portfolio. We run sensitivities, we changed the fleet to see if the benefits were still in those ranges, and we confirmed that as well. So with a different fleet, still the tranche 2.1 portfolio provides benefits that are above the 1 point benefit to cost ratio. So that map shows all the existing lines, new substations, the 345, 765 kV the new and the ones that are part of the tranche two processes. So I'll leave it here. I know there's going to be some discussions about how we went about this and the benefits of the process. But the question that I think we're still asking ourselves at MISO that wanted to share with the community here is how can we apply this to other processes so that we can incorporate uncertainty and better measure uncertainty as part of our transmission planning process. We are kind of scratching the surface a little bit with these benefits that I talked about today, but we think there are more opportunities to extend this to other processes, including potentially interregional transmission and some of the other metrics that we included here. So with that, thank you very much. I'll conclude here and looking forward to the panel.